Good evening. As you settle into stillness, imagine for a moment that the earth beneath us is not the earth we know today, not the familiar outlines of continents we see on a globe, not the vast Atlantic or the wide Pacific. Instead, imagine a planet rearranged, a world before Pangea, when the continents were scattered fragments drifting across an ancient sea, or gathered in shapes so strange they would feel like a dream if we could see them now. The rocks we walk upon are old storytellers. Each carries the memory of a world long gone, pressed into its layers like whispers frozen in stone. When we look back hundreds of millions of years, we find not just one supercontinent, but many before it: Rodinia, Gondwana, Laurussia, each with its own seas, mountains and skies. They rose, they broke apart, they drifted and rejoined. Like pieces of an endless puzzle, the earth has been playing with itself since time began. What was life like then? How did oceans without boundaries breathe? How did winds taste when the air was thick with gases we no longer know? To step into that world is to drift into an ancient dream, one both alien and familiar, where time feels slower and the silence is deeper. Welcome to Arcane Skies. If you'd like to support this journey, feel free to like, subscribe and share where and when you are listening tonight. Imagine yourself standing on a shoreline at dusk. The tide moves in with a steady rhythm, brushing against jagged rocks that have been here longer than any human memory. Their surfaces are worn, grooved, marked by time so vast that our lifetimes would vanish like a single ripple on the water compared to their endurance. The air is cool and salt-laden, and in the quiet between waves there is the suggestion of something else, a murmur, almost a voice, carried in the stillness of stone. These rocks are storytellers, and if we listen with patience, they begin to reveal the language of the earth itself. Geology, at its heart, is the study of memory. Each layer of sediment, each seam of quartz, each fossilized shell is an entry in a diary that stretches back nearly 5 billion years. When we see cliffs with bands of colour, red ironstone, pale limestone, dark basalt, we are not just looking at rock, we are reading time, 1 million years compressed into inches, a volcanic eruption recorded as a sudden black scar, a vanished ocean preserved in shells buried far from any current sea. For geologists, the earth is not silent at all. It is filled with whispers waiting to be interpreted. Before the age of Pangea, before the land we now recognise ever gathered into that single supercontinent, the stones tell us of older worlds. They hold the imprint of Rodinia, a supercontinent that existed nearly 1 billion years ago. They remember the cold silence of the Snowball Earth, when glaciers crept toward the equator and the seas themselves nearly froze. They carry traces of Gondwana, a massive landmass that stretched across the southern hemisphere, bearing strange life forms in seas that no longer exist. And even before those, they hold secrets of fragments that came together, only to drift apart again, endlessly rearranged. When we look closely, we find clues hidden in their structure. Magnetic minerals, for example, act like tiny compasses. When molten rock cools, these minerals align themselves with Earth's magnetic field at that exact moment in time. Over millions of years, as continents drift, the angle of that magnetization changes. By studying these faint signals, paleomagnetism, as scientists call it, we can map where land once lay, thousands of kilometres away from where it is now. Rocks, in other words, carry maps drawn in invisible ink, and patient study allows us to trace coastlines that vanished hundreds of millions of years ago. It is humbling to think that mountains we now see as immovable, like the Appalachians in North America or the Highlands of Scotland, were once parts of very different worlds. The Appalachians, worn and softened by time, were born of collisions that took place before Pangea, when fragments of earlier continents collided and raised peaks as high as the Himalayas. Today they are quiet hills, with forests and rivers. But in their stone hearts they still hold the heat and violence of their birth, when molten rock surged upward and pressure folded crust into ridges that touched the sky. Standing by the shore, you might wonder, how much of this is imagination and how much is memory? Is it only science, carefully measured, or do these ancient rocks hold something more, a presence that transcends their chemistry? Some cultures have long believed that stone is alive in its own way, not living as we do, but carrying a spirit of endurance. To touch a boulder shaped by glaciers is to touch the edge of eternity. To hold a fossil is to cradle a moment when a living creature, once breathed, moved, and was preserved by accident in the turning of the earth. Science tells us that continents drift because of plate tectonics, the slow circulation of heat from Earth's mantle beneath the crust. Over millions of years, land is pulled apart at rift zones, where new oceanic crust is born, and shoved together at subduction zones, where one plate dives beneath another. But there is also a poetry in this movement. Continents are dancers in a performance we cannot see in full, only glimpses in the still frames of geology. Each collision is a step, each separation a turn. The rhythm is not ours, it is measured in millions of years, but it is there, steady and ceaseless. When we try to picture Earth before Pangea, it is easy to imagine something alien, almost otherworldly. Yet perhaps the greater truth is that it was always Earth, always the same planet, with the same heart of molten iron, the same cycles of water and air. The difference lies in arrangement, in how the pieces were laid across the board. Before Pangea, there were seas without familiar names, mountains without human witnesses, skies without birds. But there was continuity too, the same sun, the same gravity, the same restless stone. And so, as you rest, consider this. Every rock beneath your feet has made a journey longer than any human voyage. It has travelled across oceans, collided with other lands, sunk deep into the mantle, and risen again. It has seen ice ages come and go, climates shift from hot to cold and back again. It has watched forests rise and be swept away. It has felt the silence of extinction and the blooming of new life. Each stone is an archive of survival. The shoreline in your mind grows darker now as the last light fades. The whisper of waves becomes softer, almost like breathing. The rocks remain, quiet and enduring, holding stories no human language can fully capture. They do not hurry to reveal themselves. Their time is different from ours, patient and slow. Perhaps in listening, we are reminded that the world is older and deeper than we can truly imagine, and that our own presence here is just another layer, thin and fleeting, on top of countless others. And so the question lingers in the night air. If stone could speak in a language we could understand, what stories of lost continents and vanished seas would it tell us? Close your eyes and picture the Earth, not as it is now, but as it was nearly 1 billion years ago. The continents were not scattered in familiar patterns, nor gathered into Pangea. Instead, they had drifted together into a different configuration, a vast landmass geologists call Rodinia. Its name comes from a Russian word meaning motherland, a reminder that it may have been the cradle for many chapters of our planet's geological story. Yet if you could stand upon it, it would not feel like a homeland. It would feel immense, silent, and strangely empty. Rodinia stretched across much of the equator, but the land was barren. Plants had not yet colonized the continents, so the surfaces were rock, sand, and dust. There were no forests, no grasses, not even moss. The only life clung to the oceans, simple organisms, algae, bacteria, carrying out the slow work of photosynthesis, releasing oxygen into the air. The sky above this ancient world may have been tinted differently than ours, with hazes of methane and carbon dioxide softening the sunlight, and clouds heavy with unfamiliar balances of moisture. To walk across Rodinia, had anyone existed to do so, would be to cross a desert without end. And then, something extraordinary happened. Around 720 million years ago, the Earth seems to have tipped into one of its most extreme climates ever known. Glaciers advanced not just across the poles, but toward the equator. Snow and ice may have covered nearly the entire planet, from mountain ranges down to the seas themselves. Scientists call this episode Snowball Earth. Imagine standing on Rodinia then, the wind sharp and dry, the land entombed under white sheets that stretched to the horizon, the silence broken only by the cracking of ice as it expanded. Oceans themselves may have frozen over, their surfaces sealed beneath kilometres of ice, leaving only dark, cold pockets of liquid water below. How could such a catastrophe occur? Some scientists point to changes in the composition of the atmosphere, perhaps a sudden drawdown of greenhouse gases like carbon dioxide. Others imagine the positions of the continents played a role. Rodinia, straddling the equator, its vast landmass reflecting sunlight back into space, cooling the planet even more. Once the ice began its advance, it may have fed on itself, a feedback loop of reflection and cooling, until the Earth was trapped in its own frozen mirror. For life, it must have been an unimaginable trial. Photosynthetic organisms, those that depended on sunlight, would have struggled beneath the ice. But in the dark, in the depths of the sea, life adapted. Chemosynthetic bacteria, living on chemical reactions around undersea vents, carried on. Tiny refugees beneath thin sheets of ice or near geothermal heat may have become sanctuaries, and it was in these desperate conditions that the seeds of complexity may have been nurtured. Some researchers believe that the challenge of surviving the Snowball Earth forced life into new experiments, laying the groundwork for the more complex forms that would bloom later. It is haunting to imagine a planet nearly silenced, locked in a deep freeze for millions of years. Imagine the creak of glaciers sliding over stone, the endless night of an ice-covered ocean, the stars burning above a frozen equator. No birds, no leaves, no human warmth, only the persistence of microorganisms, clinging invisibly to life. In such silence, the Earth itself might have seemed dead to an outside observer. And yet, beneath the ice there was patience. Life endured. Eventually, the freeze began to thaw. Volcanic eruptions spewing carbon dioxide into the atmosphere may have slowly warmed the planet. As greenhouse gases built up, the ice retreated, rivers returned, seas opened, and the world breathed again. And when the thaw came, it may have come suddenly, in a rush of melting that transformed climate, flooding coastlines and washing nutrients into the seas. For life, it was as if the planet had been given a second chance, a renewal after catastrophe. Rodinia itself would not last. Over tens of millions of years, the great supercontinent began to fracture. Rifts opened, seas spilled in, and land masses drifted away. The Earth had entered a new cycle of assembly and separation, the endless pattern of supercontinents forming and breaking apart. What remained, however, was the lesson of Snowball Earth, that our planet is capable of extremes far beyond our daily imagination, and that life, fragile yet stubborn, finds a way through even the most impossible trials. Tonight, as you listen, It is easy to think of ice as something simple, a block in your glass, a crust on a winter road. But ice can be a world, it can be an ocean, a continent, even a prison. And in the deep past it became the canvas upon which Earth painted one of its most dramatic experiments. The rocks still whisper of that age. In Namibia, in Canada, in Australia, we find layers of cap carbonatites, sudden deposits that formed when the ice melted, and chemical reactions flooded back into the seas. They are the signatures of a world that was frozen, then reborn. And each time a geologist cracks open such stone, they are listening to the faint echo of that ancient thaw. It raises a question as soft as snow. If life could survive a world locked in ice for millions of years, what else might it survive? And if Earth itself could be so strange, so extreme, so alien to our senses, then how many other worlds, circling other suns, might be waiting with their own frozen silences, their own whispered survivals? Imagine standing at the edge of an ocean, unlike any we know today. The water is not the familiar blue we see when we look at modern seas, but a shifting palette of colours, greenish where algae blooms cluster, reddish where iron and sulphur dominate, dark and nearly black in places where oxygen is absent. The air above carries a sharp tang, metallic and sour, as if the sea were exhaling minerals instead of salt. This is not the ocean of gentle tides and coral reefs, but an ancient ocean, deep and strange, a cradle of life, and yet a reminder of how alien our own planet once was. Billions of years ago, before plants and animals flourished, Earth's oceans were chemical theatres. They were heavy with dissolved iron, sulphur compounds, and other minerals leached from the restless crust. Oxygen was scarce. For much of this time, free oxygen, the kind we breathe, barely existed in the atmosphere. Instead, the seas were ruled by microbial kingdoms, especially cyanobacteria, tiny architects of transformation. By capturing sunlight through photosynthesis, they released oxygen as waste, slowly altering both sea and sky. What we take for granted today, the invisible breath of the world, was once a revolutionary toxin, poisonous to the anaerobic organisms that had thrived in its absence. Picture the shoreline at dusk, mats of microbial colonies spread across tidal flats like strange living carpets, slimy and layered, each surface coloured with different pigments to capture the faintest rays of sun. These were stromatolites, living rock-like structures, some of the earliest cities built by life. Their growth was slow, yet relentless, building domes and mounds that resisted waves. If you were to run your hand across them, you would feel a texture both organic and mineral, a bridge between stone and life. In the deeper waters, other microbes thrived by chemical means. Some consumed iron, leaving behind banded iron formations, alternating layers of dark and light that hardened into rock, still visible today in cliffs and quarries. These bands are not just decoration, they are history, a record of how the oceans once rusted as oxygen reacted with dissolved iron, falling to the seafloor in vast deposits. Every slice of banded ironstone is a frozen page from a book written in a time when life was microscopic but already reshaping the planet. Yet even in this alien chemistry, beauty found a place. Imagine the waters illuminated not by fish or corals, but by glowing bacteria, bioluminescent signals shimmering in the darkness. Perhaps it was not a silent world, but one filled with invisible conversations, chemical whispers exchanged in currents, light flickers beneath waves, the slow spread of oxygen like a tide of change. The climate of these ancient oceans was no less strange. Without large continents covered in vegetation, weathering worked differently. Carbon dioxide built up, then dropped, often in wild swings. Periods of warmth followed by plunges into cold seas created cycles of stress and renewal. Storms may have lashed empty coasts with rains, unlike those of today, falling on bare stone and running into rivers tinted red with iron. Each drop carried the scent of minerals, as if the world were brewing itself anew. And still, life persisted, tiny, simple, often invisible, but enduring. The strange chemistry of the seas may even have been the testing ground for greater complexity. Some researchers suggest that it was in oxygen-poor but chemically rich waters that the first eukaryotic cells with nuclei and organelles, found a niche. These more complex cells would eventually give rise to plants, animals, and us. But in those early times, they were fragile experiments, like sparks flickering against the vast ocean night. It is humbling to think that our own ancestry passes through such seas. Our cells carry mitochondria, tiny powerhouses that were once independent bacteria, absorbed into larger cells in a moment of cooperation rather than conquest. This quiet partnership, forged in the depths of strange ancient oceans, became the foundation of all complex life. Without that merging, without that evolutionary gamble, the oceans might still be ruled only by mats of microbes, and the earth might never have known forests, animals, or human voices. As you drift deeper into this vision, imagine floating on a small raft upon those ancient waters. The horizon is endless, but the silence is unsettling. No gulls cry overhead, no fish leap in the air, only the sound of waves against your vessel and the distant gurgle of gas bubbles rising from seafloor vents. At night, the stars above are brilliant, but the sea beneath is alive with its own light, faint glows from microbial colonies shimmering in streaks like fireflies trapped in water. It feels both lonely and full, empty and alive. Science explains this as chemistry and biology, the slow work of molecules and time. But from a more human perspective, it almost feels like myth. The oceans were not only mothers of life, but also guardians, testing resilience, demanding adaptation, shaping futures. One could imagine them as vast ancient spirits, silent yet vigilant, ensuring that only those forms of life willing to change could survive. Even now, the evidence remains in rock. In Greenland, in Western Australia, in South Africa, ancient ocean sediments are preserved, holding isotopes and mineral traces that whisper of the strange balances that once prevailed. Geologists read them carefully, tracing oxygen levels, chemical cycles, shifts in temperature. Each sample is a portal, a reminder that what we see as ordinary blue seas are only the latest chapter in a story written in salt, mineral, and time. And so, as you rest tonight, consider this. The oceans we know, the Pacific, the Atlantic, the Indian, are but fleeting arrangements. They will open and close, vanish and reappear. But before Pangea, before even Gondwana or Rodinia, the seas were strangers still, and yet from their alien chemistry came the breath we now draw in comfort. The question that lingers is gentle yet vast. If such alien seas once existed here on Earth, what oceans, equally strange and silent, might be glimmering right now on distant worlds circling other suns? Picture the Earth not as a fixed stage, but as a restless performer, forever shifting its stance. Beneath the familiar crust where we live, rivers of molten rock circulate in slow motion, like invisible tides moving over spans of millions of years. This circulation, rising and falling like breath, pulls at the surface above, cracking it open in places, welding it together in others. Continents, which we sometimes imagine as eternal, are in truth rafts of stone drifting upon this hidden current. They collide, fracture, and drift again in a cycle as steady as the heartbeat of the planet itself. After Rodinia began to weaken, around 750 million years ago, rifts opened across its expanse. Imagine standing upon that ancient land and hearing, not instantly, but over generations, the sound of Earth tearing itself apart. Valleys widened, deepened, and filled with seawater, until the land that had once been whole became scattered fragments. Oceans pushed into the wounds, forming new coastlines and birthing new seas. To us, such changes feel almost unthinkable. Yet for the Earth, they are as natural as breathing in and out. Geologists today can trace these moments in the patterns of rocks. Basaltic lava flows, frozen black rivers of ancient magma, line places where the crust once tore open. Thick wedges of sediment tell of basins that formed as land pulled apart, collecting the dust and shells of vanished eras. Even the orientation of minerals, the faint magnetism they carry, reveals how continents rotated as they drifted from one configuration to another. To study them is to read not only what broke, but how it drifted, turning the planet into a puzzle constantly rearranging itself. The breaking apart of continents is not simply destruction, it is also creation. When land drifts, it gives birth to new ocean floors, mid-ocean ridges, vast chains of undersea mountains rise where magma pushes through, solidifying into crust that expands outward, like the seams of a growing garment. The Atlantic Ocean, which feels to us like it has always been there, was once a narrow crack in the supercontinent Pangea. Slowly, persistently, that crack widened, becoming a sea, and then an ocean. Someday, in the unimaginable future, it too will close again, as continents converge elsewhere. What is it like in the imagination to witness such a birth? Perhaps you would stand at the edge of a rift valley, the ground trembling softly underfoot. Heat rises in shimmering waves from fissures in the crust. Sulphur and smoke billow upward, tinging the sky with strange colours. Rivers change course, diverted into deepening basins. Over centuries, lakes appear, salty and brimming with microbial life. These lakes widen, merge, and one day the horizon opens to reveal an ocean where once there was only land. Life responds to these transformations in ways both subtle and profound. Oceans newly born create fresh habitats, shallow seas where sunlight reaches the seafloor. These places become laboratories of evolution, warm nurseries for new forms of life. Conversely, when continents collide, mountains rise and climates change, forcing organisms to adapt or vanish. The very pattern of extinction and renewal that shapes the story of life is linked to this tectonic dance. It is easy to think of continents breaking apart as violent, but in truth it is an almost imperceptible motion. A few centimetres a year, slower than fingernails grow, is enough to rearrange the face of the planet over time. We might imagine an abrupt tearing, yet no single moment defines the split. It is a slow drifting, a patient unfolding, like watching a crack form in ice across a frozen lake, inching outward, day after day. To the Earth, it is neither sudden nor slow, it is simply its way. Standing in the present, we sometimes forget that the land beneath us is moving, even now. GPS satellites can measure the drift, Africa inching northward toward Europe, the Americas edging westward, Australia sailing north. Someday, millions of years ahead, the continents will collide again, forming another supercontinent with a new name. Just as Pangea once gathered, and Rodinia before it, so too will this unnamed future world emerge. We live in only a single chapter, unaware that the pages keep turning. There is also mystery in these motions. Why does Earth alone, among all the planets we know, have such an active crust, broken into plates that wander across its surface. Venus and Mars, though rocky like ours, seem frozen in comparison. Perhaps it is Earth's size, or its water, or some delicate balance of heat and composition. Whatever the reason, our world is a wanderer, its continents never content to remain where they are. This restlessness has sculpted every landscape we know. The Himalayas from collision, the Pacific from separation, the Andes from subduction. Without this movement, Earth would be silent stone. With it, Earth is alive. As the night deepens, think of the continents not as fixed homelands, but as voyagers. They travel so slowly that no human will ever perceive their journeys. Yet if we could speed time forward, we would watch them drift like clouds across the surface of the planet, colliding, parting, swirling into new forms. The coastlines we know would vanish, mountains would rise and erode, seas would open and close, and in each reshaping, new stories of life would be written. The rocks beneath your feet, the mountains on the horizon, the seas that lap against shores, all are part of this great migration, and it leaves us with a lingering image, Earth as a restless dreamer, forever shifting, forever remaking itself, the continents floating like islands of memory upon a sea of fire. So the question lingers, in the quiet, if the land beneath us is always moving, do we ever truly stand still? Drift now, in your imagination, to a world 600 million years in the past. The land is gathered not into Pangea, but into another giant, a supercontinent that geologists call Gondwana. Its form sprawls across the southern half of the globe, stitching together what will one day be South America, Africa, Antarctica, India, and Australia. If you could look from above, there would be no familiar outline of continents, no map you could recognize, only a massive, asymmetrical shape, set against a single, endless ocean. The climate here is strange. In some regions, glaciers spread across what is now Africa, carving deep valleys into bedrock. In others, deserts stretch under a pale sky. The sun is the same as today, but the air feels different. Oxygen levels are rising compared to earlier ages, but the atmosphere still carries more carbon dioxide than we could breathe comfortably. The winds sweep dry dust from vast inland plains, while coastlines, long and broken, are washed by ancient tides that carried whispers of something new. Because on Gondwana, life is beginning to change. For billions of years, the world's living things were simple: bacteria, algae, small colonies invisible to the naked eye. But here, in the late Precambrian seas, a new form of life emerges, larger, more complex, and delicate in ways that seem almost dreamlike. These were the Ediacaran organisms, named after the hills in Australia, where their fossils were first found. Their forms were unlike anything alive today. Imagine lying in shallow water at the edge of Gondwana, the seafloor beneath you soft with microbial mats. In the dim light, you might see flat, frond-like shapes rising gently, swaying with the currents. Some look like ferns pressed into stone, though they are not plants. Others resemble discs or ribbons, their bodies quilted with repeating patterns. A few are as wide as a dinner plate, others stretch several feet across. They have no bones, no shells, no mouths, no eyes. They absorb nutrients directly from the water or from the mats they rested upon. To us, they seem both alien and familiar, like living imprints of leaves drifting between the worlds of biology and geometry. Fossils of these beings are found not as bones, but as impressions, delicate outlines pressed into ancient sandstone. When paleontologists uncover them, they appear like shadows of dreams, faint, otherworldly, as if the rock had remembered the shape of something that passed across it for only a moment. Some are simple circles, others branch into complex fractals, repeating patterns like frost on a window. They leave us guessing. Were they animals, plants, or something else entirely? A separate kingdom lost to time? The Ediacaran world carried its own silence. No fish darted through the water. No predators hunted with teeth. Instead, it was a slow, drifting existence. Mats of microbes covered much of the seafloor, feeding the gentle grazers that lay upon them. There were no jaws, no skeletons, no shells scraping against one another. It was a world before conflict, or perhaps simply before the kind of conflict we recognise. Yet even in this quiet, something was stirring. Evolution was experimenting. Some forms of Ediacaran life hint at movement, faint traces of grooves left in sediment, as though they had shifted across the mats in search of food or light. Others may have floated, catching currents. Still others hint at division and reproduction, patterns suggesting colonies or budding growths. The stillness was deceptive. Beneath it, the machinery of change was accelerating. From Gondwana's coasts, storms swept nutrients into shallow seas, fueling these organisms. Oxygen levels crept upward, opening new possibilities for metabolism. Perhaps it was this rise in oxygen that allowed larger bodies to form, sustained by more efficient energy use. Whatever the cause, life was no longer content to remain microscopic. The stage was being set for the explosion of diversity that would come in the Cambrian period, only a few tens of millions of years away. Standing in imagination on Gondwana's shoreline, you might see glaciers in the distance, their white tongues reaching toward the sea. Rivers of meltwater pour into the ocean, carrying minerals that feed blooms of algae. The air is sharp and cold, and the land is empty. No trees, no grasses, not even moss clinging to stone. Only bare rock and ice broken by winds, stretching as far as the eye can see. And yet just offshore, in shallow water, an invisible drama unfolds. Life experimenting with form and structure, laying the groundwork for all future complexity. Some scientists describe the Ediacaran period as a failed experiment. Most of these forms vanish at the dawn of the Cambrian, replaced by harder, more mobile creatures with shells, skeletons, and eyes. But perhaps it is unfair to call them failures. They were the first step into a new world of possibility, proof that life could grow beyond invisibility, that it could weave itself into shapes large enough to cast shadows. Without them, the later explosion of diversity might never have come. Their fossils remind us that evolution is not a straight line, but a branching river. Many streams dry up, but their water nourishes the currents that continue. When we hold a slab of sandstone marked with an Ediacaran imprint, we are not holding the memory of failure, but of a door half opened, an invitation into a wider world. And so, Gondwana becomes not just a landmass, but a backdrop, a silent witness to life's first attempts at grandeur. Its glaciers, its deserts, its barren coasts, all were part of the canvas. And in shallow seas along its shores, organisms painted patterns of life that still linger in stone, fragile and faint yet profound. As you rest tonight, let the image linger. An empty continent under strange skies, a cold wind sweeping dust across the land, and in the quiet waters nearby, soft fronds swaying in currents, like the earth itself, breathing for the first time in a new way. And the question drifts into silence. If these ghostly forms could whisper to us across 600 million years, what lessons of beginnings and endings might they share? Imagine standing on a cliff above an ancient sea, long before forests, long before birds filled the skies. The air around you feels heavy, unfamiliar. It is not the air you breathe tonight, fresh and balanced with oxygen. Instead, it carries a sharpness, tinged with gases that would sting the lungs of any modern creature. The winds sweep across the bare rock, whistling through valleys with no trees to break their sound. This was the atmosphere of Earth before Pangea, a sky in transition, restless and alive in ways we can scarcely imagine. For much of our planet's early history, oxygen was scarce. Instead, gases like carbon dioxide, methane, and nitrogen dominated. Volcanoes breathed them out in constant exhalations, filling the sky with a haze that tinted the light. The faint warmth of the young sun was trapped by these gases, preventing the Earth from freezing solid. In those days, the air itself was both shield and danger, preserving warmth while poisoning many early life forms. Over time, life began to alter the very air that sustained it. Cyanobacteria, tiny architects of change, released oxygen as a byproduct of photosynthesis. At first, this oxygen was soaked up by iron in the oceans, forming vast deposits of banded ironstone. But as the iron became saturated, oxygen began to spill into the atmosphere. Slowly, the sky was transformed. What had once been toxic to most forms of life became a new possibility. Breathing, as we understand it, was born from this shift. But in the times just before Pangea, the balance was still delicate. Oxygen levels rose and fell dramatically. During the Carboniferous period, for instance, oxygen concentrations may have been far higher than today, fueling the growth of enormous insects and dense, swampy forests. Yet in earlier periods, oxygen was still unstable, waxing and waning like the tides. To breathe in such an atmosphere, had you stood there, might have been dizzying, overwhelming, or even deadly. The winds that carried this air across the planet were no less important. Without large forests or grasses, dust and sand moved freely, sculpting landscapes with relentless patience. Imagine storms sweeping over Gondwana, their gales filled with fine particles of silt and grit. Every gust carried the breath of volcanoes, the scent of sulphur, and the trace of minerals. Rain, when it fell, smelled metallic, heavy with dissolved elements washed from bare stone. The cycle of erosion and renewal was written not in green leaves but in the dialogue between wind and rock. And yet, even in this alien atmosphere, life found ways to adapt. Microbes clustered in sheltered pools, forming mats that altered local chemistry. Shallow seas became laboratories, where oxygen was patchy, abundant in some places, absent in others. These gradients drove diversity, pushing organisms to evolve in ways that mirrored the shifting winds above. The atmosphere and life were locked in conversation, each shaping the other, each responding in turn. To imagine this world is to picture a sky of different colours. Perhaps sunsets blaze deeper, with the scattering of methane hazes, glowing orange and red in ways we cannot see today. Perhaps dawn carried a thicker, softer light, diffused by volcanic dust. The stars above, though the same, might have twinkled through veils of unfamiliar gases, giving the night sky a strange shimmer. Every breath of wind, every curtain of cloud, was part of a stage unlike the one we know. Scientists trace these shifts in ancient rocks. Sulfur isotopes trapped in sediments speak of low oxygen skies. Layers of coal and shale tell of times when oxygen surged, feeding vast forests that in turn changed the air again. The Earth's atmosphere has never been still. It has always been a restless companion, shaping life and shaped by it. When we think of atmosphere, we often think of fragility, the thin veil of gases clinging to a planet, the narrow margin that makes life possible. And it is fragile. Strip it away, as happened on Mars and life struggles to persist. Thicken it too much, as on Venus, and the planet becomes a furnace. Earth's atmosphere, with all its changes, has always walked a delicate line. And before Pangea, that line was drawn by winds carrying whispers of both death and possibility. Close your eyes for a moment and imagine yourself in that world. The ground beneath you is bare, raw stone. The wind howls, sharp with grit. The sky above is tinted, the light hazy, carrying the scent of sulphur and iron. Breathing is difficult. Every inhalation is heavy. Yet nearby, in a shallow tide pool, microbial mats shimmer with life, glowing faintly with the pigments of photosynthesis. Even in a sky alien to us, the seeds of the familiar world are there, waiting to unfold. It is a reminder that the air we take for granted, the invisible, effortless breath of tonight, was not always here. It was made by countless generations of tiny organisms, slowly rewriting the atmosphere. Their work set the stage for forests, animals, and eventually us. Every breath we draw carries their legacy, an inheritance written not in words but in the chemistry of the sky. And so the question lingers on the wind. If the air we breathe today is only one chapter in a long story of change, what colours, what scents, what strange compositions will the skies of Earth carry in ages yet to come? Now let your imagination drift outward, beyond the borders of any single land, until only water stretches before you. Picture an ocean, so vast it encircles nearly the entire planet. No Pacific, no Atlantic, no Indian or Arctic seas, just one continuous body of water, endless and unbroken. This was Panthalassa, the world ocean that wrapped itself around the continents before and during the assembly of Pangea. Its name means all sea, and it was a realm so immense that even today our minds struggle to grasp it. Standing on Gondwana's shoreline, or perhaps on one of the northern land masses drifting toward it, you would see no opposite coast. The horizon would be pure water, curving away into infinity. Storms would roll across this vastness with unimaginable power, waves building for thousands of kilometres before breaking upon a shore. The winds, unobstructed by mountains or forests, howled across its surface. The ocean itself was a universe, its currents circulating heat, salt, and life around the globe. Beneath its surface, Panthalassa was no empty desert. It teemed with early marine life, from trilobites crawling on the seabed to strange fish armoured in plates of bone. In some regions, coral-like structures were beginning to build reefs. Not yet the colourful gardens we know today, but fragile bastions where life experimented with shelter. In the deeper waters, predators like anomalocarids still lingered from earlier ages, chasing soft-bodied prey in the shadows. And always, the microbes, the unseen architects, filled the water, shaping its chemistry with their invisible labour. The ocean's currents told their own story. Modern scientists, using models and the clues left in rocks, suggest that Panthalassa's circulation may have been both simpler and more extreme than our own oceans. Gigantic gyres, vast circular currents, may have carried heat from equator to pole, shaping climates on distant continents. Nutrients upwelled from the deep in slow cycles, feeding blooms of plankton that turned the water green in places, red in others. Every wave, every tide was part of a planetary heartbeat, regulating temperature and life. It is easy to think of such a sea as monotonous, yet Panthalassa was filled with contrasts. Shallow continental shelves, warmed by sunlight, glowed with life. Here armoured fish swam among mats of algae, and soft-bodied creatures grazed upon microbial carpets. But farther out, the open ocean stretched in silence. Imagine drifting in a small vessel, carried for months with no land in sight. Days bled into nights, the sky mirrored in water, until horizon and sea became indistinguishable. For early life, this vastness was both opportunity and danger, an open stage where evolution could experiment, but also a realm where extinction could sweep across with little warning. Storms on Panthalassa must have been extraordinary. With no continents to interrupt them, cyclones could spin larger and more violent than those we know today. Lightning would illuminate the endless sky, thunder rolling across open water, waves cresting taller than towers. Yet after each storm, calm returned, the ocean settling back into its timeless rhythm. The cycle of chaos and stillness mirrored the pulse of Earth itself. The ocean floor beneath Panthalassa was just as restless. Mid-ocean ridges, fueled by heat from the mantle, pushed crust outward, widening the sea even as continents drifted. Subduction zones, where plates sank back into the earth, birthed chains of volcanoes that dotted the ocean's expanse with islands. Imagine a volcanic island, black with fresh basalt, steam rising where lava met water, a lonely outpost in an infinite sea. Such islands became stepping stones for life, places where shallow lagoons formed and new ecosystems took root. When we study Panthalassa today, we do so through the scattered fragments left behind. Most of its seafloor has been recycled back into the earth by tectonic processes, but bits remain in mountain belts and ophiolite complexes, slices of ocean crust stranded on land. In their minerals, in their chemistry, we read the faint echoes of that ancient sea. They tell us of spreading ridges, of magnetic reversals recorded in basalt, of sediments laid down in waters that no longer exist. Each fragment is a puzzle piece, a reminder that oceans too are temporary, though they seem eternal to us. Panthalassa also played a role in life's great dramas. Its vastness connected ecosystems, spreading species across the globe. But it also magnified catastrophe. When extinction events struck, volcanic eruptions, shifts in climate, or disruptions in circulation, the consequences rippled through Panthalassa's waters, affecting life everywhere. To live within this ocean was to be part of a single, interconnected web, fragile in ways we are only beginning to understand. And yet Panthalassa was not merely destructive, it was a cradle. Its shallow shelves nurtured the ancestors of fish, amphibians, and eventually all terrestrial animals. Its depths sheltered life through crises, keeping it alive when the surface world faltered. In its endless reach, it carried resilience as well as danger. Close your eyes and listen to it now. Hear the hiss of wind across waves that never end, the crash of breakers on unseen shores, the deep hum of water moving in gyres across a planet without boundaries. Imagine the stars above, reflected perfectly on its surface, as if the sky itself had fallen into the sea. For early creatures, Panthalassa must have felt like eternity, an infinite expanse where time and space dissolved into water. As you breathe slowly, consider the paradox. Oceans, for all their vastness, are also fragile. They change with chemistry, with currents, with climate. They nourish life, but they also hold the power to extinguish it. Panthalassa reminds us that no sea, however immense, is forever. Even the all-sea eventually gave way. Its waters divided into the oceans we know today. And so the question drifts like a tide. If Earth once carried a single ocean that encircled everything, might it one day return to such a state when continents merge again and the seas unite into one vast mirror of the sky? Imagine walking across a continent where the ground is damp with ancient rains and the air feels thick with moisture. The year is more than 400 million years ago, and the land before you is part of Laurussia, also called Euramerica, a continent born when smaller land masses collided. It stretches across the northern hemisphere, forming as pieces of what will become North America and Europe, fused together in slow tectonic embraces. Its coastlines are jagged, its interior vast and uncharted, its skies heavy with clouds that feed rivers flowing towards shallow seas. Something remarkable is happening here. For the first time in Earth's history, land is beginning to turn green. Where once there was only bare stone and sand, now primitive plants are spreading outward. Moss-like carpets hug the edges of streams. Small vascular plants, simple stems with spores instead of seeds, rise timidly from damp soil. They are fragile, delicate, no taller than your ankles. Yet in their presence, the land begins to feel different, less barren, more alive. As time passes, these pioneers are joined by something new, the first true trees. Imagine towering Archaeopteris, one of the earliest of them. Its trunk rises high, thick and woody, its branches spreading outward like fans. Its leaves are not leaves as we know them, but fronds, delicate yet abundant, drinking in sunlight. Forests begin to spread, covering valleys and slopes, their roots digging deep into the ground, breaking stone into soil, altering the very chemistry of Earth. For the first time, shade falls across the land, cast not by cliffs or mountains, but by living things. The arrival of forests transforms everything. Roots stabilize riverbanks, slowing erosion. Fallen leaves and branches decay, creating rich layers of organic matter. The air itself changes, oxygen levels climbing as these new forests exhale into the sky. The atmosphere thickens with life's breath, making it easier for creatures in water and on land to thrive. Oxygen may have risen so high that insects grew to astonishing sizes. Dragonflies with wingspans as wide as a hawk's. Millipedes stretching longer than a human arm. The forests were not silent. They hummed with the rustle of leaves, the calls of early amphibians, the hum of giant insects. Laurussia's climate, shaped by its latitude and the great ocean Pantalassa, oscillated between warm periods and cooler intervals. In swampy lowlands, vast wetlands formed, their waters choked with vegetation. When plants died here, they often fell to decay fully, sinking into mud where oxygen was scarce. Over millions of years, this built up layers of peat that would, under pressure and time, transform into coal. The coal deposits of today's Europe and North America are the compressed ghosts of Laurussia's ancient forests, still carrying the carbon of leaves that once reached toward Devonian skies. If you could stand within one of these early forests, it would not look exactly like the forests you know. There would be no flowering plants, no grass beneath your feet. Instead, the ground would be soft and spongy with mosses and decaying fronds. The trees would seem alien, their shapes unfamiliar, their spores drifting in clouds rather than seeds falling in shells. Streams would wind through undergrowth of strange plants, and in their shallows, fish with primitive lungs might surface briefly to gulp air. Amphibians with limbs half-formed might drag themselves from water to land, their wet bodies glistening under a dim sun. This world was one of transition. The forests gave rise to new ecological niches, new possibilities. For the first time, animals had shade and shelter on land. For the first time, soil could sustain more than microbes. The air, thick with oxygen, offered energy for bodies to grow larger, stronger. Evolution responded, experimenting with forms that would shape the future. Yet Laurussia was also restless. Its formation was not peaceful but violent, born of collisions that raised mountains. Where Europe and North America met, mountain chains rose, folded and crumpled by tectonic pressure. These ranges, though worn now, once towered like the Himalayas. They shaped climate and river systems, directing rainfall, guiding winds, carving valleys that became cradles for forests. To walk through them then would be to move through a landscape, both raw and fertile, where stone and life wrestled for dominance. Scientists today read this story in the rocks of Appalachia, in the Caledonian mountains of Scotland and Scandinavia. Their folded layers, tilted and twisted, are records of the collisions that stitched Laurussia together. Fossils of plants pressed into shale, imprints of early forests, and seams of coal speak of the greening of the earth. In every ridge and valley, the memory of Laurussia lingers, even though the continent itself has long since been reshaped, broken apart, and scattered across the globe. The transformation that began with Laurussia was irreversible. Once forests had taken root, the planet could never be the same. Oxygen levels, soil formation, and the carbon cycle were forever altered. The land was no longer a barren extension of oceanic crust, but a living system in dialogue with the sea and sky. Life had stepped fully onto land, and in doing so, it changed the Earth's destiny. Close your eyes and imagine the sound of wind through the first forests. Not the complex chatter of modern woods, but a simpler chorus, the creak of tall fronds swaying, the patter of spores drifting like dust, the distant splash of amphibians retreating into streams. Light filters through primitive canopies, softer and dimmer, tinged with the haze of an atmosphere, still adjusting to its new chemistry. You walk slowly, each step sinking into damp ground, surrounded by forms both alien and familiar. You are witnessing the Earth's first attempt at making land truly alive. And as the night deepens, a question remains, carried on the breath of ancient leaves. When the first forests spread across Laurussia, did the Earth feel its own transformation? Did it know, in some silent way, that it had entered a new chapter of life? Drift with me now into a time before fish swam with jaws, before forests shaded the land, before shells hardened into armour. The seas of the late Precambrian were inhabited by creatures so strange that even with fossils in hand, we can scarcely decide what they were. They belong to a forgotten menagerie, a gallery of forms that seem at once organic and geometric, alive yet ghostly. They are often grouped as the Ediacaran biota, but to speak their name is to admit we still do not truly know them. Imagine wading into a shallow lagoon 580 million years ago. The water is clear but dim with sunlight filtered through haze. On the seafloor lies a carpet of microbial mats, slimy and soft, the foundation of this alien ecosystem. Resting on those mats are shapes that stir the imagination. One lies flat like a frond pressed into stone, its body a series of quilted ridges radiating outward. Another resembles a ribbed oval, its form neither animal nor plant, but something in between. Still another rises gently from the seafloor, swaying like a leaf in an unseen breeze. They do not swim, they do not hunt, they simply exist, absorbing nutrients through their surfaces, passive and yet enduring. Some look like discs, no larger than a coin. Others stretch meters across, delicate patterns etched into their bodies as though drawn by a careful hand. They bear names given by modern scientists, Dickinsonia, Spriggina, Charnia discus, but the names feel inadequate, unable to capture the enigma of their nature. Were they animals? Were they giant colonies of single-celled organisms? Were they experiments of evolution, branches on the tree of life that grew for a while and then withered away? When paleontologists uncover these fossils, they find impressions rather than bones. Soft-bodied creatures leave no skeleton, no shell, only the faint shadows of their forms pressed into sandstone. To hold such a slab is to hold a memory, as though the earth itself remembered a dream and inscribed it into stone. They remind us that life does not always follow a path we can recognize. Sometimes it drifts into possibilities we cannot name, creating shapes that vanish as suddenly as they appeared. And yet these forms mattered. They marked the first large organisms, the first time life grew beyond invisibility. For billions of years, everything had been microscopic. Suddenly here were creatures big enough to leave imprints, to shape ecosystems, to alter sediments, as they rested on microbial mats. The scale of life changed, and with it, the possibilities of evolution expanded. The Arcane Seas were quiet. There were no predators with teeth, no swift swimmers chasing prey. Instead, life unfolded slowly, peacefully, each organism finding its place in the tapestry. But quiet worlds do not last forever. As oxygen rose and ecosystems grew more complex, new players emerged. By the Cambrian, just a few million years later, animals with eyes, skeletons, and jaws would appear. In comparison, the Ediacaran creatures seemed fragile, almost ephemeral, and indeed most of them vanished, leaving no descendants that we can clearly trace. But perhaps we should not judge them by survival alone. For tens of millions of years, they thrived in their own way, filling seas with forms that challenged the imagination. They remind us that evolution is not a straight march toward modernity, but a vast exploration of what is possible. Some paths continue, others end, but each leaves a trace. Without the Ediacaran experiment, perhaps the explosion of life in the Cambrian would never have been possible. Scientists still debate their nature. Some argue they were early animals, precursors to jellyfish, worms, or arthropods. Others see them as a unique kingdom, a lineage that left no heirs. Still others imagine they were symbiotic colonies, blurring the line between individual and community. Their ambiguity is part of their power. They are mirrors that reflect our uncertainty, reminders that not all mysteries can be solved by names and categories. Close your eyes and imagine walking along a tidal flat in that age. The ground beneath your feet is soft, patterned with faint ridges. The tide is out, leaving pools of water where frond-like creatures still wave gently. The air is quiet, the only sound, the faint lapping of waves. In this stillness, you sense a presence both alien and familiar. You're walking among the earliest experiments of complexity, surrounded by forms that lived and died before forests, before animals, before history itself. When we gaze at their fossils today, framed in museum cases or etched into desert cliffs, we are struck not only by their strangeness, but by their delicacy. They are like pressed flowers from a forgotten book, fragile yet enduring across nearly 600 million years. They whisper to us of a time when life had no blueprint, when it shaped itself freely, without rules or expectations. And so the image lingers, an ocean floor covered in quilted forms, silent and still, like a meadow of ghostly ferns beneath the waves. They have no eyes to see, no voices to call, yet they were the first to leave a mark large enough for us to find. And the question drifts in the quiet. If life today vanished and only its impressions remained, what would distant beings think of our shapes, our patterns, our brief experiment in time? Let the ocean around you shift again. The soft, ghostly creatures of the Ediacaran world fade, and in their place, something new stirs. It is the dawn of the Cambrian period, about 541 million years ago. The seas are suddenly alive with movement, colour and competition. What was once a quiet meadow of quilted fronds becomes a bustling metropolis of creatures, each stranger and more intricate than the last. Scientists call this event the Cambrian explosion, a phrase that captures both its suddenness and its abundance. For in just a few tens of millions of years, life diversified more rapidly than at almost any other time in Earth's history. Imagine standing on the floor of a Cambrian sea. The water is clear, illuminated by shafts of sunlight that reveal a scene of astonishing variety. Trilobites, armoured like living shields, scuttle across the sand. Their segmented bodies glisten in the light, their many legs working in synchrony as they graze on algae or burrow for food. Some are small as coins, others stretch nearly as long as your arm. Around them dart small shrimp-like creatures with jointed limbs and delicate antennae, feeling their way through currents. But it is not just the familiar forms that fill these waters. Here swims Anomalocaris, one of the earliest great predators. Its body undulates gracefully as it propels itself forward, with flaps along its sides, almost like a ribbon. At the front are two grasping appendages, curved like sickles, ready to seize prey. Its circular mouth, lined with plates, opens and closes like a camera shutter, capable of crushing shells. To the trilobites, Anomalocaris was a nightmare, a hunter unlike anything that had existed before. Elsewhere, sponge-like creatures filter water, pulling in tiny particles. Worms tunnel through the sand, leaving trails behind them. Creatures with hard shells drift slowly, protected by their armour. And above, small organisms with primitive eyes catch glimpses of light, detecting movement in ways that change everything. Sight itself has arrived, and with it, the dance of predator and prey intensifies. This sudden abundance raises questions that scientists still puzzle over. Why did life diversify so quickly in the Cambrian after remaining relatively simple for billions of years? Some point to rising oxygen levels, which allowed for larger, more active bodies. Others suggest the breaking apart and rejoining of continents created shallow seas, rich in nutrients and sunlight. Still others see the invention of eyes and mobility as a spark. Once creatures could see and chase. Once they could burrow and hide, evolution accelerated into a spiral of innovation and defense. Whatever the cause, the Cambrian explosion was a turning point. Almost every major animal group that exists today, arthropods, mollusks, chordates, can trace its lineage back to this time. It was as if life had discovered a new vocabulary, and suddenly the sentences of evolution grew longer, richer, more elaborate. The fossils of this age capture the strangeness vividly. In the Burgess Shale of Canada, in the Chengjiang deposits of China, exquisite impressions reveal soft tissues as well as shells. We see creatures like Hallucigenia, a spiny worm that once baffled scientists, first drawn upside down with its spines mistaken for legs. We see Opabinia with 5 eyes perched on its head and a long proboscis ending in a claw. We see Wewaxia covered in scales and spines, gliding across the sea floor like a living puzzle. Each fossil is a reminder that evolution is not neat or predictable. It is a wild experiment, trying forms both elegant and bizarre. To imagine yourself there is to be overwhelmed by movement. Trilobites march in lines across the sand, their carapaces shining. Worms wriggle through silt, stirring clouds that drift upward. Above, Anomalocaris glides silently, its eyes scanning, its appendages flexing. Light filters down, broken by the rippling surface, illuminating scenes that feel almost mythic. It is a world neither empty nor quiet, but brimming with possibilities. And yet it is also fragile. Many of the Cambrian creatures vanished, their lineages ending almost as quickly as they began. Others endured, slowly refining their forms into the ancestors of modern animals. The explosion was not a permanent burst, but a wave, spreading, breaking, and reshaping life's trajectory. In our time, when we hold a trilobite fossil in our hands, we are not only touching stone, we are holding the memory of this revolution. Its ridges and segments are the echoes of a time when the rules of life changed forever. To look into its tiny compound eyes is to glimpse one of the earliest experiments in vision, a sense that would alter ecosystems for all time. The Cambrian explosion is sometimes described as life's great awakening, but perhaps it is better imagined as a dawn. After billions of years of night, the sun rose suddenly and revealed a horizon crowded with forms. Some lasted, others faded, but the brightness of that dawn never entirely dimmed. Everything that came after, forests, dinosaurs, mammals, humans, was built upon the foundations laid in those seas. Close your eyes and let the scene soften. Hear the muffled clicks of trilobites against sand, the faint currents stirring through fronds of sponge-like creatures, the swift rush of Anomalocaris moving unseen. The ocean hums with life, a symphony of movement and adaptation, and above it all, light filters through water, fractured and golden, as though the sea itself were glowing with possibility. And so the question drifts gently across time. If life could bloom so suddenly, so abundantly, from near silence into symphony, what other explosions of possibility might still await in the future, hidden just beyond the horizon of time? Imagine walking through a valley where the air is cool and thin, and the horizon is broken not by low hills, but by towering ridges that seem to scrape the clouds. These are not the mountains we know today. They belong to an earlier Earth, a world where continents were still colliding, drifting, and remaking themselves long before Pangea came into being. Mountains, after all, are not eternal. They are born, they rise, they crumble, and they vanish. But in their brief lives, they shape the planet's climate, its rivers, and its story. When continents collide, stone folds like cloth under immense pressure. Layers that once lay flat at the bottom of seas are forced upward, tilted into ridges, stacked into peaks. Imagine two rafts drifting on a lake, colliding slowly, but with unstoppable force. Their edges crumple and rise. In the same way, land masses like Laurentia, Baltica, and Avalonia collided hundreds of millions of years ago, giving birth to mountain ranges that rivaled the Himalayas. These were the Caledonian orogenies in what is now Europe, and the Appalachian orogenies in North America. To stand there then would be to hear stone groan. Earthquakes would shiver through valleys. Rivers would reroute as ground lifted beneath them, and volcanoes would erupt where crust sank deep and melted. From such violence came beauty, snow-capped peaks, high plateaus, cliffs where waterfalls tumbled down freshly raised stone. It was a landscape in motion, its drama measured not in days but in millions of years. Mountains are not only sculptors of stone, but also of air. As these ancient ranges rose, they changed weather itself. Moist winds from Pantalassa and other seas struck their slopes, rose upward, and cooled, shedding rain. On one side, valleys filled with rivers and lakes. On the other, dry rain shadows formed, birthing deserts. This pattern still shapes our world today, from the Himalayas casting shadow on Tibet to the Andes shaping the Amazon. Long before Pangea, the same forces were at work, the same dialogue between mountain and sky. The rocks of these early mountains carried secrets too. Fossilized shells, now found high in the Appalachians, tell us that their stone was once seafloor, thrust upward by tectonic collisions. Minerals formed deep underground were lifted into sunlight, where they glittered against glaciers and rivers. Every ridge was a monument to pressure and heat, to stone reshaped in the furnace of Earth's restlessness. Imagine walking along a ridge at dawn. The air is crisp, carrying the scent of volcanic ash and pine-like plants beginning to colonize the slopes. Streams rush downward, cutting ravines that will widen over ages into valleys. Far below, swamps spread across the lowlands, where amphibians croak and dragonflies with wings like sails glide between trees. From such mountains, rivers carried sediments that nourished wetlands, swamps, and forests. Mountains fed life, even as they stood in austere silence. But mountains are mortal. Over time, wind and water grind them down. Peaks that once towered, rivaling the Himalayas, wear into gentle hills. The Caledonian Range, once titanic, is now reduced to the Scottish Highlands. The Appalachians, born of collisions before Pangea, are now rounded ridges, their once jagged summits softened into green slopes. To us they feel old, but in truth, they are only remnants, the bones of mountains that once touched the stars. Their erosion also shaped the world. As rivers carried dust and gravel away, sediments filled basins and shallow seas, preserving fossils of the plants and animals that thrived nearby. These layers became pages of Earth's diary, pressed into stone. Coal seams, limestone beds, and shale deposits, all are gifts of mountains that once stood tall, then crumbled into soil and sand. Even in their decay, mountains gave life. Scientists can still trace these events in the fabric of the Earth. By analysing minerals that only form under extreme pressure, they know how deep rocks were buried before being raised. By measuring isotopes, they can tell the temperatures that forged crystals. Each grain of stone carries a story of collision, of fire, of uplift. Mountains are storytellers as much as they are landscapes. For ancient peoples, mountains would one day become symbols of eternity, places where gods dwelled, peaks that touched heaven. But in the age before Pangea, they were only stone, fresh and raw, unmarked by myth, yet already sacred in their scale. Imagine standing in their shadow, a small figure on a restless earth, watching clouds coil around their summits. You would not name them, but you would feel their power in your bones. As you breathe slowly, let the image of those mountains settle. See glaciers sliding down their flanks, carving valleys that would one day become fertile plains. Hear rivers rushing, carrying boulders that clatter and grind, smoothing themselves into pebbles that will rest on distant shores. Smell the damp earth where forests begin to root in cracks of stone. These are the mountains before Pangea, cradles of rivers, forges of minerals, guardians of skies. And as night deepens, a quiet thought rises. If mountains can be born and die, if even stone is impermanent, what then does permanence mean? Is anything truly eternal on this restless earth? Close your eyes and imagine the earth breathing, not in the span of seconds or minutes, but in the span of ages. Warmth rising, then fading, glaciers advancing, then retreating, forests spreading, then shrinking into memory. These are the rhythms of climate, cycles so vast we often mistake them for permanence, yet they are only patterns in a dance that has gone on since the planet was young. Long before Pangea, before dinosaurs, before even the first forests, Earth's climate was already pulsing between extremes. The evidence is written in stone, striations carved into bedrock by ancient glaciers, layers of sediment dropped where ice once melted, isotopes in fossil shells that record the temperature of seas. These tell us of times when the planet grew cold enough for ice to creep across continents, and of times when warmth flooded back, leaving green worlds in its wake. One of the most profound examples is the Snowball Earth episodes, when ice may have reached the equator, covering nearly the entire planet. We have already passed through those frozen dreamscapes in earlier parts of this journey, but even after the great freeze thawed, Earth's climate did not settle into stillness. Instead, it continued its restless oscillations. Around 450 million years ago, during the Ordovician period, another great glaciation unfolded. The supercontinent Gondwana drifted across the southern pole, and ice sheets spread across what would one day be Africa, South America, and Antarctica. Seas retreated, exposing continental shelves, while cold waters shifted currents and altered ecosystems. The result was a mass extinction, one of the first great crises of life, as many marine species vanished. Imagine shallow seas that had once teemed with trilobites and corals suddenly cooling, their warmth stolen by advancing ice. Life had flourished, and then, in the span of geological moments, it faltered. Why do these cycles happen? Part of the answer lies in the heavens. Earth's orbit is not fixed. It wobbles, tilts, and stretches over time. These changes, called Milankovitch cycles, alter how sunlight reaches the planet, sometimes favouring warmth, sometimes cold. Over millions of years, these orbital rhythms amplify or diminish the effects of greenhouse gases, volcanoes, and ocean currents. The result is a climate that has never been still, always moving between extremes. Volcanoes, too, have left their mark. In some ages, vast eruptions poured gases into the sky, filling the atmosphere with carbon dioxide. The planet warmed, seas rose, and forests spread. In other ages, eruptions shrouded the sky in ash, reflecting sunlight, cooling the earth. Imagine standing beneath such a sky, dim, orange-tinted, the light filtered through volcanic haze. The air would taste acrid, the land cooler, the seas responding in slow but steady shifts. Climate is not a single force, but a chorus of influences, orbital cycles, volcanic breaths, the drift of continents, the whispers of life itself. Before Pangea, these rhythms shaped both land and sea. Warm periods brought lush coastal environments where early amphibians ventured onto land. Cold intervals contracted ecosystems, pushing life back into refuges. Evolution responded to both bounty and scarcity. Species adapted, diversified, or disappeared, leaving their stories written in fossils. The great forests of the Carboniferous period, dense and humid, were products of high oxygen and warm climates, while their eventual decline was tied to shifting temperatures and drier air. Climate is not just background, it is the stage and the director of life's drama. Imagine an Ordovician shoreline as ice begins its slow advance. The waves are edged with frost, glaciers gleam in the distance, and the air carries a sharp chill. Creatures in the shallows retreat or perish, their shells piling into sediments that will one day become limestone. Far away in warmer waters, survivors adapt, their lineages carrying forward. The rhythm of climate is both merciless and generous. It takes, but it also reshapes, opening space for the new. Even today, geologists can trace these cycles in rock. Oxygen isotopes in tiny fossils record ancient sea temperatures. Coal seams speak of swampy, warm worlds, glacial deposits of cold epochs. The Earth is an archive, each layer another measure of its long breathing, and though the details are intricate, the pattern is clear. The planet is never fixed, never steady. It shifts between warmth and cold, between abundance and scarcity, a pendulum swinging across eons. For us, living in a moment of warmth, it is hard to imagine ice advancing across continents, but such events have happened repeatedly. The great glaciers of the Ordovician, the Devonian, the Carboniferous, all came before Pangea. Each time life adjusted. Each time the world remade itself. And each time the cycle continued, indifferent to the fleeting span of individual creatures. There is a quiet lesson here. What feels eternal, the forests, the seas, the climate itself, is only temporary, a phase in Earth's restless rhythm. The continents drift, the winds shift, the seas rise and fall. We live in a brief interlude of stability, but the pendulum still swings. The same cycles that sculpted life before Pangea will continue long after us. Close your eyes and hear it. The sound of ice grinding across stone, slow and heavy. The trickle of meltwater carving valleys. The roar of volcanic eruptions altering the air. The whisper of winds carrying dust from deserts into seas. This is the music of climate, patient and powerful, setting the tempo for all life on Earth. And the question lingers in the night, if the Earth has always breathed in cycles of warmth and cold, what chapter of that breath are we living in now? And how long will it last? Imagine lowering yourself into a shallow sunlit sea some 430 million years ago, in the middle of the Silurian period. The water is warm, clearer than the nutrient-rich seas of earlier ages, and the bottom is alive with new structures rising from the sediment. These are the world's first coral reefs, primitive, fragile, but already weaving together frameworks of life. Their delicate skeletons are not yet as complex as modern corals, but they create ridges and towers where none had existed before. For the first time, the sea has architecture, places of refuge, hunting grounds, and nurseries. Drifting through this new underwater city, you would see a host of creatures finding homes in its crevices. Trilobites scuttle along the bases, seeking food among detritus. Small mollusks cling to surfaces, filtering water. Worms wiggle between tiny caves, safe from predators. Above, schools of jawless fish, agnathons, swim gracefully, their bodies armoured in bony plates, their mouths little more than circular openings. They are awkward compared to the sleek fish of later ages, but they are pioneers, learning what it means to be vertebrates in a world still dominated by invertebrates. For hundreds of millions of years, life had been confined mostly to soft bodies, fragile, easily erased by time. But now skeletons and armour are becoming more common. Shells grow thicker, plates harden, spines appear. It is as if the Cambrian arms race has continued, but with refinement. Defence and offence are becoming subtler, more durable. The Silurian seas are not as explosively strange as the Cambrian, but they are steadier, richer, and more interconnected. The reefs themselves transform the environment. By slowing waves and trapping sediments, they create lagoons, calmer waters, where delicate life can thrive. They also pump oxygen into the ecosystem, sustaining more creatures than barren seafloors ever could. Imagine swimming above such a reef. Colours glimmer faintly, light refracted in ripples, small fish darting in and out of shadows. It is not yet the rainbow spectacle of modern coral reefs, but it is a beginning, a promise of the worlds to come. On the seafloor beyond the reefs, new plants are taking root. Simple vascular plants begin to creep from shallow waters onto land, their stems stiffened by lignin, a molecule that gives strength. They are tiny, no taller than grass blades, but they represent a revolution. For the first time, land is not entirely barren. Green begins to spread along riverbanks and coastlines, catching the light, stabilizing soils, and altering the chemistry of the air. Soon, these plants will prepare the way for forests. But in the Silurian, they are only pioneers, delicate threads binding land to sea. Life above water is still sparse. The land is quiet, home to little more than fungi and moss-like mats. Yet in tidal flats and marshes, strange arthropods, early scorpion-like creatures, begin to explore. Their exoskeletons shield them from the dry air, their gills still tied to water, but they represent the first hesitant steps of animals beyond the sea. Imagine one of these creatures crawling across damp sand, leaving a faint track that will fossilize into stone, a signature of courage in miniature. Back in the water, something extraordinary is happening among the fish. While most remain jawless, simple filter feeders or scavengers, a few lineages begin to experiment with new structures. Their mouths evolve hinges, teeth, the ability to bite and hold. The first jawed fish appear, tiny at first but carrying a potential that will change the course of evolution forever. With jaws comes predation, more precise and powerful, and with predation comes diversity. As prey evolve new defences in turn, the cycle of innovation spirals onward. The Silurian seas also resonate with climate stability. After the Ordovician glaciation, temperatures have warmed again, sea levels have risen, and shallow seas flood continents. Warm waters spread across Laurussia and Gondwana, creating habitats ripe for expansion. This relative calm allows life to diversify steadily, without the harsh interruptions of massive extinction. For millions of years, reefs grow, fish spread, and plants creep further inland. It is a period of balance, of quiet growth, like the steady unfolding of a long breath. Imagine drifting through those seas at sunset. The water glows golden, beams of light filtering through ripples and casting shifting patterns on the sandy floor. Jawless fish glide silently in schools, their armoured heads flashing in the light. Tiny reef structures rise like miniature fortresses, their surfaces alive with worms, corals and sponges. The silence is broken only by the faint clicking of trilobites and the distant swish of predators stirring the water. In the shallows, green plants wave gently, their spores drifting into the breeze. It feels both ancient and new, fragile and eternal. When scientists uncover Silurian fossils, they find a world in transition. Coral reefs that prefigure modern ecosystems, fish that foreshadow sharks and bony fish, plants that promise forests, arthropod tracks that hint at terrestrial life. Each fossil is a doorway, a reminder that even slow periods in Earth's history are filled with quiet revolutions. Evolution is not always an explosion. Sometimes it is a steady hum, like waves against a shore, shaping the world grain by grain. Close your eyes and let that hum wash over you. The steady lap of ancient waves, the swaying of the first plants in the breeze, the shadow of armoured fish gliding in silence. The sea in this age is neither barren nor crowded, but balanced, a world learning how to sustain complexity. And as the night deepens, a gentle question arises. In the reefs and shallow waters of the Silurian, did life already sense the land calling, waiting to be claimed, promising new worlds beyond the tide? Now imagine walking across the land 380 million years ago. The silence that once defined the continents has begun to fade. Where once there were only mosses and small stems hugging riverbanks, now forests spread outward, covering valleys and slopes with a richness Earth had never known. This is the Devonian period, sometimes called the Age of Forests, when green first truly conquered the land. The pioneers are strange by modern standards. Great tree-like plants such as Archaeopteris tower overhead, their trunks woody and thick, their frond-like leaves fanning into the sky. They are not quite like the trees we know, lacking seeds and flowers, but they rise tens of meters high, forming the first canopies in Earth's history. Beneath them grow dense thickets of ferns and horsetail-like plants, their spores drifting in the humid air. For the first time, the land is shaded, the soil cool and dark beneath a green roof. Forests are not just scenery, they are engines of transformation. Their roots dig deep, breaking down rock, releasing minerals, and creating true soil. As roots spread, they anchor the land, slowing erosion. Leaves fall, decay, and enrich the earth, building layers of organic matter. The chemistry of the atmosphere shifts too. Oxygen levels rise as photosynthesis scales upward, while carbon dioxide falls, cooling the planet. The earth, once bare and grey, becomes a living system where air, soil, and life entwine. Close your eyes and breathe in this ancient forest. The air is moist, tinged with the smell of wet ferns and decaying leaves. Insects buzz through shafts of filtered light. Giant dragonflies, with wings wider than your hand. Early arachnids, exploring the littered ground. The forest hums with energy, a pulse of life spreading into niches never before filled. For the first time, ecosystems on land rival those in the sea. In the rivers and lakes winding through these forests, fish flourish in astonishing variety. The Devonian is also known as the Age of Fishes, for here sharks, armoured placoderms, and lobe-finned fish thrive. Some of these lobe-finned fish carry lungs as well as gills, their fins muscular enough to push through shallow water. In swampy shallows, they gulp air when oxygen runs low, or drag themselves across mudflats. Out of these experiments, evolution shapes the first amphibians, creatures with limbs sturdy enough to support them on land. Imagine one of these animals, eyes just above water, body glistening, hesitating at the edge before stepping forward into ferns. A world that was once silent now rings with its first croak. Forests also fuel climate change on a planetary scale. By drawing carbon dioxide out of the air and locking it into wood, the forests cool the earth. Over millions of years, this cooling will contribute to glaciations and even extinctions. Life is not only adapting to the planet, it is reshaping the planet itself. Forests are engineers as much as they are inhabitants. Yet the Devonian forests were not permanent in their form. Many of the plants that dominated lacked seeds, relying on spores that needed water to reproduce. This tied them to damp environments, even as they grew into mighty trees. The first seed-bearing plants, small and inconspicuous, began to emerge during this time, carrying within them the potential for a new revolution. Seeds could survive dry conditions, spreading life into arid lands far from rivers. Though humble at first, seeds would one day allow forests to conquer deserts, mountains, and every climate the earth offered. Walking through a Devonian forest would feel alien. There are no flowers, no bird calls, no mammals rustling in the underbrush. The air hums with insects, millipedes longer than your arm, spiders experimenting with silk. Amphibians croak near streams, their shapes halfway between fish and salamanders. The forest floor is damp and cluttered, spongy with decaying fronds, its soil rich but primitive. Above, the canopy filters light into a dim green glow. It is both familiar and strange, a place that whispers of what forests will become but still belongs to another age. Fossil evidence from places like Gilboa in New York shows us petrified stumps of these first great forests. Their roots spread wide, their trunks thick and strong. In these fossils we see the earliest ecosystems where tall plants dominated, where animals lived in their shade and where rivers began to snake through fertile valleys. The forest, once a dream, became a structure, an enduring presence on land. The Devonian ended not in stillness, but in upheaval. Climate cooling, driven partly by forests, led to extinctions in the seas. Reefs collapsed, many fish lineages vanished, and ecosystems shifted. The forests endured, but they too would change, evolving into new forms as time pressed forward. The legacy of this age, however, was permanent. The earth had turned green, and it would never be bare again. As you lie back tonight, imagine walking slowly through that first forest. Sunlight flickers through tall fronds. The air is heavy, rich with oxygen. A dragonfly glides past, its wings glinting in the glow. At your feet, amphibians stir in damp soil, their tracks etched into mud. You are surrounded by beginnings, of forests, of rivers fed by roots, of animals venturing onto land. The Earth is no longer only a blue planet, it has become a green one. And the question lingers in the shadows of those ancient trees. When the Earth first learned to breathe through forests, did it also dream of the future? When green would cover every corner of its restless surface? Picture a shallow lagoon at dusk, its surface glimmering gold with the last rays of sun. Along its muddy banks, something stirs, an animal neither fully of the water nor yet of the land. It pushes its body forward with strong fleshy fins, leaving grooves in the wet sediment. Its head lifts above the surface, eyes blinking in the open air. It pauses, then drags itself further, each movement clumsy, uncertain, but determined. This is one of the first amphibians, a pioneer in one of evolution's most daring experiments, life stepping onto land. For millions of years, lobe-finned fish had been testing the boundary between water and air. Equipped with lungs as well as gills, they could survive in stagnant pools, where oxygen was scarce, gulping air from above. Their fins, muscular and jointed, allowed them to push along the bottom of rivers or across muddy flats. These traits, born of necessity in unstable environments, became the tools of transformation. From them emerged animals like Tiktaalik, with wrists strong enough to bear weight, necks flexible enough to lift their heads, and bodies bridging the divide between fish and amphibians. The land they entered was no longer barren. Forests of ferns, horsetails, and early trees shaded the banks. Insects buzzed in the air, some of them giants, dragonflies with wingspans nearly a metre wide, millipedes as long as a human. The soil was damp and soft, rich with decaying plant matter. For an amphibian climbing from water, the world above was humid, green, and filled with opportunity. Food was abundant, predators were few, and the air was thick with oxygen. But the challenges were immense. Gravity weighed heavier than water's buoyant embrace. Skin dried quickly, without constant moisture. Movement was awkward, every step an experiment in balance. To survive, these pioneers needed to remain close to water, returning often to lay their eggs and keep their skin moist. Yet with every generation, adaptations grew stronger. Limbs lengthened, lungs became more efficient, senses adjusted to both water and air. Life was learning a new way to exist. Imagine walking along a Devonian riverbank as night falls. The air is warm, damp with the scent of ferns and moss. You hear the faint rustle of movement, an amphibian pushing through undergrowth, its body glistening with moisture. Its call is a low croak, simple but new, a voice rising into a world that had never known such sound. On the ground nearby, insects scatter at its passing, while overhead, dragonflies hover like silent sentinels. The forest is alive with beings that no longer belong solely to the sea. The arrival of amphibians reshaped ecosystems. For the first time, vertebrates, animals with backbones, were no longer confined to water. They began feeding on insects, creating new food chains. Their presence also pressured plants and arthropods to adapt, fueling an ongoing cycle of interaction and innovation. Land, once the domain of plants and invertebrates, became a stage for vertebrate life, setting the foundation for reptiles, mammals, and ultimately humans. Fossil evidence captures this story vividly. Footprints pressed into ancient mud reveal the hesitant steps of amphibians along shorelines, their toes splayed, their stride uneven. Bones of early species such as Acanthostega and Ichthyostega show creatures that still carried traits of fish, gills and tails for swimming, but also had limbs strong enough for crawling. They were neither fully one thing nor the other, but in between, proof that evolution is not about sudden leaps, but about gradual bridges. Their existence also reveals a profound truth. Life does not advance in perfect foresight. These creatures did not climb onto land knowing they would one day give rise to reptiles and mammals. They were simply adapting to their circumstances: oxygen-poor water, predators in the shallows, food on land, and yet in their adaptation lay the seeds of the future. What began as survival became the foundation of new worlds. Close your eyes and imagine the silence of that ancient night, broken only by the soft chorus of amphibians calling to one another from the water's edge. Their voices echo across forests newly grown, carrying over rivers and into valleys. It is a sound both tentative and triumphant, as if the earth itself were testing a new language. In those croaks and rustles is the beginning of the terrestrial symphony that will one day include birdsong, mammal calls, and human speech. The Devonian forests and their amphibian inhabitants remind us that boundaries are not barriers. The line between water and land was once absolute, but life blurred it step by step. Each movement onto mud, each adaptation of lung and limb, each fragile egg laid near the water's edge was part of a long negotiation. And from that negotiation came permanence. Life had found a way to be at home, not only in the sea, but also upon the ground. Over time, amphibians would diversify, some returning more often to water, others venturing further inland. They would face competition, extinctions, and transformations. But the path had been opened, the door unlocked. Once life had crossed the threshold of land, it would never fully retreat. As you breathe slowly, picture the glow of fireflies drifting through the shadows of that primeval forest, their light mingling with the calls of amphibians. Picture the ripple of water as a creature surfaces for air, then pushes forward onto land. The night is alive with possibility, the earth dreaming itself into new forms, and a question lingers, quiet as the steps of those first wanderers. When the first amphibians gazed upon forests and skies, did they sense they were leaving one world behind, or did they simply follow an instinct that carried them unknowingly into the future? Now imagine a world thick with mist, where the air itself feels heavier, richer. It is 320 million years ago, during the Carboniferous period, and oxygen levels in the atmosphere are higher than at any other time in Earth's history. With nearly 35% oxygen compared to today's 21%, the very air fuels life in extraordinary ways. Forests are dense and sprawling, stretching across vast lowland swamps. The ground is soft, waterlogged, layered with peat and fallen fronds. The air hums with the movement of wings, giant insects gliding and buzzing in the heavy atmosphere, their bodies larger than nature allows today. The trees are unlike the ones we know. Towering lycophytes and horsetails, some rising over 30 metres, dominate the swamps. Their trunks are tall and straight, covered in patterns of diamond-shaped scars where leaves once clung. Their crowns burst into tufts of greenery, more like giant ferns than modern trees. Beneath them, smaller ferns and seed ferns weave a dense understory. There are no flowers, no fruits, no grasses, only spore-bearing plants and the earliest seeds beginning their quiet revolution. The forest floor is a labyrinth of roots and decaying matter, damp and rich, alive with fungi, and the scuttling of arthropods. In this lush setting, insects grow to remarkable sizes. Meganeura, a dragonfly-like predator, soars through the air with wingspans wider than a hawk's. Millipedes longer than a car, Arthropleura, crawl slowly through the undergrowth, their many legs moving in hypnotic waves. Spiders the size of dinner plates prowl in the leaf litter, and scorpions nearly a metre-long hunt along swampy banks. Oxygen fuels their growth, allowing respiratory systems that would collapse today to sustain massive forms. The carboniferous air is a greenhouse for giants. Amphibians thrive here too, no longer confined to the water's edge. Some grow large and diverse, their bodies well suited to swampy forests. They hunt insects and fish, laying eggs in moist environments. Their calls echo through the wetlands. At night, a chorus carried on heavy, humid air. But a new lineage is also emerging, creatures with eggs that can survive away from water. The amniotes, ancestors of reptiles, birds and mammals, are taking their first steps. Their shelled eggs protect embryos from drying out, allowing them to colonize drier habitats far from swamps. It is a quiet revolution, one that will shape the destiny of all terrestrial life. The carboniferous world is not only a biological marvel, but also a geological one. In the stagnant waters of its swamps, plant material falls, piles, and fails to fully decay. Over millions of years, layer upon layer of this organic matter compresses into peat, then into coal. Entire forests, pressed by time and stone, become black seams buried beneath the earth. These coal beds, still mined today, are the preserved breath of the carboniferous forests, sunlight captured in carbon and locked away for hundreds of millions of years. To hold a piece of coal in your hand is to hold the memory of ancient trees, dragonflies and amphibians, compacted into a fragment of the past. Climate during the Carboniferous oscillates between warm, humid intervals and cooler glacial episodes as Gondwana drifts across the southern pole. Yet the greenhouse effect of the forests is profound. By absorbing carbon dioxide, the trees cool the earth, stabilizing conditions and fueling glaciations. The planet is breathing deeply, exhaling oxygen and inhaling carbon, reshaping its climate in ways no planet without forests could. Life itself has become a geological force. To walk through a carboniferous swamp would be to enter a dreamlike world. The canopy stretches high above, blotting out much of the sunlight, casting the forest floor into twilight. The air is thick with moisture, fog hanging between trunks. The ground squelches with every step, soft with peat and roots. Giant insects hum past, their wings vibrating in low, droning tones. Amphibians slither through shallow pools, their bodies breaking the surface with slow ripples. Occasionally, the earth shakes as Arthropleura crawls by, its armoured body glinting faintly in shafts of filtered light. It is a world of giants, not in scale of continents, but in the creatures that breathe the heavy air. Scientists piece together this vision from petrified forests, fossil insects, and coal seams spread across Europe, North America, and Asia. Stumps of lycophytes still stand fossilized in quarries. Imprints of giant millipede tracks stretch across sandstone slabs. Wings of dragonflies are preserved in exquisite detail, their delicate veins like stained glass windows frozen in time. Each fossil tells us this was not imagination, but reality, a world that once thrived where now there are only stone and dust. Yet even this lush age was not eternal. By the end of the Carboniferous, climates began to shift. The great swamps contracted as drier conditions spread. Many of the giant insects and amphibians declined, unable to adapt to falling oxygen, and changing ecosystems. Reptiles with their amniotic eggs and hardy bodies took their place, better suited to the new world to come. The age of forests was ending, but its legacy was carved into the earth. Coal seams deep beneath our feet, oxygen-rich memories in the very air we breathe. As you rest tonight, picture that humid forest at dusk. The mist is rising, the canopy dark against a glowing horizon. The sound of wings fills the air, deep and resonant, as giant dragonflies circle above. In the distance, a chorus of amphibians croaks from the water's edge, their calls echoing through the swamp. You step carefully, the ground soft and wet, the air heavy with the scent of ferns and decay. It is a world both alien and familiar, a dream that once was real, and a question lingers like fog among the trees. If we could breathe that ancient air, dense with oxygen and heavy with life, would we feel exhilaration? Or would we feel the weight of a world too full of breath to bear? Now let the swampy forests of the Carboniferous fade, their dragonflies and giant millipedes dissolving into mist. In their place rises a new world, drier, harsher, and stranger. It is the Permian period, beginning around 299 million years ago, and the Earth is shifting once again. Gondwana and Laurussia are drawing closer, the slow tectonic drift preparing the way for Pangea. As land masses converge, seas shrink, climates harden, and life learns to adapt to an increasingly unforgiving stage. The seas of the Permian are vast and diverse. Along the edges of Panthalassa, shallow waters bloom with coral-like organisms, sponges and brachiopods, shell-bearing creatures that filter the waves. Rugose corals, crinoids waving their feathered arms, and ammonites with coiled shells fill reef-like communities. Fish swim above, some sleek and cartilaginous like early sharks, others armoured with scales glinting in the light. The open waters carry great predators, swift and efficient, their bodies honed by millions of years of refinement. Life in the seas has reached a richness that rivals even the Cambrian explosion, but with a stability and complexity never seen before. Yet beneath this flourishing surface, the land is changing. The humid swamps of the Carboniferous are gone, replaced by drier forests, scrublands, and deserts. Oxygen levels have fallen, no longer supporting giant insects. Amphibians still thrive near rivers and lakes, but their dominance wanes. In their place rises a new lineage of vertebrates, the reptiles. Reptiles carry with them a revolutionary gift, the amniotic egg. Encased in protective shells and membranes, their eggs can survive away from water, allowing them to colonize drier environments where amphibians cannot. This freedom transforms them. They spread across landscapes once inhospitable, their bodies scaled against desiccation, their lungs efficient in the thin air. Small lizard-like creatures scurry through underbrush, while larger forms lumber across open plains. Some grow into predators with sharp teeth and powerful jaws. Others become herbivores, their bodies broad and heavy to digest tough plants. Imagine standing in a Permian desert at dawn. The air is cool but dry, carrying the scent of dust and resin. Low shrubs and seed ferns dot the land, their roots clinging to poor soil. From behind a rocky outcrop, a reptile emerges, Dimetrodon, with a great sail rising from its back, supported by elongated spines. It is not a dinosaur, but a synapsid, a distant cousin on the branch that will one day lead to mammals. The sail may help regulate temperature, warming the creature in the morning sun or cooling it in the heat of midday. Its eyes scan the plain, jaws lined with serrated teeth, a predator of its age. Nearby, herds of herbivorous reptiles graze on hardy plants, their stocky bodies armoured against attack. Smaller lizard-like creatures scuttle in the shadows, feeding on insects and seeds. This is no longer the lush greenhouse world of the Carboniferous. It is a place of survival, of adaptation to dryness, a preview of the challenges that life will face again and again on Earth. The Permian also saw innovation in the seas. Marine reptiles had not yet emerged, but fish and invertebrates filled niches with dazzling variety. Ammonites coiled upward in elegant spirals, their shells patterned with ridges and sutures. Brachiopods spreading carpets across the seafloor, their shells opening and closing in unison with the tide. Sharks patrolled deeper waters, while reefs, built of sponges and algae, grew tall and intricate, offering shelter to countless small creatures. The Permian seas were ecosystems of abundance, intricate and balanced, teeming with life that would seem familiar and alien all at once. But even as these worlds thrived, subtle signs of strain appeared. Climates grew increasingly arid as Pangea assembled, creating vast deserts in the planet's interior. The seas, though full of life, were vulnerable to changes in circulation and chemistry. Oxygen levels in the atmosphere fluctuated, challenging species that had once flourished. The Earth was restless, and beneath its surface, pressure was building in ways that would soon reshape everything. To imagine the Permian is to hold two truths at once. On one hand, it was an age of grandeur, reptiles rising, seas full of diversity, ecosystems complex and interwoven. On the other, it was a world precariously balanced, vulnerable to shifts beyond the control of life itself. Close your eyes and picture that desert once more. Dimetrodon basks in the early light, its sail glowing crimson as the sun rises. Far away, in shallow seas, ammonites drift gently, their tentacles exploring the water. Coral gardens sway, filled with tiny fish weaving in and out of shadows. For a moment, it feels eternal, stable, complete. And yet we know from the evidence of stone that this balance will not last. The greatest extinction in Earth's history lies ahead, poised to sweep away nearly all of what thrives in these scenes. For now, however, the Earth rests in this fragile equilibrium, teaching us that even flourishing worlds can be but interludes. And the question drifts through the silence of the Permian winds. When reptiles first stretched across dry land, did they sense they were pioneers? Or were they only following instincts, unaware that they were stepping into the future of all vertebrate life? Now let the Permian deserts fade from view. The reptiles, the reefs, the ammonites, the sprawling forests of seed ferns, all dissolve into silence. For the Earth is approaching one of its darkest hours, a catastrophe so profound that it will erase nearly all life. We call it the Permian Triassic extinction, or more simply, the Great Dying. It began quietly, as many cataclysms do. Deep within the crust of what is now Siberia, magma began to surge upward, erupting in vast floods of lava. These eruptions were unlike anything humans have ever witnessed. They lasted not days or months, but hundreds of thousands of years. Layer upon layer of basalt spread across millions of square kilometers, forming what geologists now call the Siberian Traps. With every eruption, gases were released, carbon dioxide, methane, sulfur compounds, altering the atmosphere. The air thickened with heat-trapping gases, the climate warmed, and the oceans began to change. At first, reefs collapsed. The intricate sponge gardens and coral structures of the Permian seas could not survive the rising temperatures and the shift in chemistry. As volcanic gases dissolved into water, the oceans grew more acidic, weakening shells and skeletons. Oxygen levels in the seas plummeted, creating dead zones where once there had been abundance. Imagine swimming in those waters, fish gasping at the surface, invertebrates lying motionless, currents sluggish and lifeless. The seas, once filled with colour and movement, became still and suffocating. On land, forests withered under relentless heat, rainfall patterns shifted, deserts spread across the heart of Pangea, and rivers dried into cracked valleys. The air grew heavy with carbon dioxide, warming the planet to levels that scorched ecosystems. Plants declined, insects faltered, amphibians dwindled. The reptiles that had flourished in the early Permian struggled as their food sources vanished. Survival became a question not of strength, but of endurance against a world unraveling. Fossil evidence tells the scale of this disaster. More than 90% of marine species disappeared. Trilobites, which had endured since the Cambrian seas, vanished forever. Rugose corals, crinoids, and many brachiopods all gone. On land, nearly 70% of vertebrate species perished. Dimetrodon and its kin, once dominant predators, vanished. Whole lineages were erased, as if the tree of life had been pruned nearly to its roots. The Earth itself seemed poisoned. Some scientists believe vast quantities of methane were released from the seafloor as temperatures rose, amplifying the greenhouse effect. Others suggest volcanic gases thinned the ozone layer, letting ultraviolet radiation scorch the surface. Whatever the exact combination, the result was devastation on a planetary scale. To imagine this moment is to picture silence. Forests once filled with insects, and amphibians stand empty, their trunks blackened by drought. Riverbeds lie dry, their stones cracked beneath a searing sun. In the seas, reefs collapse into rubble. Ammonites drift lifeless, fish vanish into the gloom. The air is heavy, hot and still. The earth feels hollow, its breath stolen, its surface a shadow of what it had been. And yet even here, life did not vanish entirely. Some species endured. Small reptiles adapted to harsh conditions, hiding in burrows or surviving on meagre resources. Certain fish and invertebrates clung to refuges in cooler waters. Microbes, resilient and unyielding, continued their invisible work. The earth had been emptied, but not silenced completely. From this near obliteration came a paradox. The destruction of so many lineages cleared ecological space for what would come next. In the Triassic period that followed, survivors diversified rapidly, filling niches left vacant by extinction. Among them were the ancestors of dinosaurs, crocodiles, and mammals. The Great Dying was both an end and a beginning, a doorway through which evolution stepped into new worlds. Scientists read this story not in myth but in rock. Black shales rich in carbon tell of anoxic oceans. Ash layers in sediments mark the volcanic fury of Siberia. Fossil assemblages reveal the abrupt disappearance of entire groups. Isotopes of carbon and oxygen shift dramatically, recording the sudden warming and acidification. Each piece of evidence is a voice, whispering of a time when Earth nearly lost itself. Close your eyes and feel the weight of that silence. The forests gone, the seas barren, the skies hazed with volcanic dust. It is a sobering image, a reminder that even a planet as resilient as Earth has known fragility. And yet, out of that darkness, life endured. The story did not end. Perhaps the lesson of the Great Dying is not only about loss, but also about resilience. Life does not move in straight lines. It falters, it suffers, it collapses, and yet it rises again. The earth remembers its wounds, but it also remembers its recovery. As you drift deeper into rest, picture the faint resilience of that moment. A small reptile burrows into the soil, surviving on scraps. A fish lingers in a cooler current, waiting for seas to heal. A plant sends up a fragile shoot after fire and drought. From such small survivals, new worlds will one day bloom. And the question drifts like smoke from ancient volcanoes. If life could endure the great dying, what might it endure still across all the ages yet to come? Imagine the silence after a storm, the way the air feels hollow, emptied of sound. Now stretch that silence across millions of years. The great Permian extinction has passed and the earth is scarred. Oceans, once teeming with life, are barren in places, reefs collapsed into rubble. Forests that once shaded the land are gone, their trunks blackened, their roots turned to ash. The planet breathes again, but faintly, like a patient recovering from a fever. It is here, in this aftermath, that survivors begin to stir. The seas, though diminished, still carry life. Tiny bivalves cling to sediments, filtering water. Ammonites, though reduced in diversity, persist, their coiled shells drifting through currents. Fish remain, some small and hardy, their gills adapted to oxygen-poor water. In quiet refuges, communities endure, waiting for conditions to improve. Slowly, reefs begin to reassemble, not with the same organisms as before, but with new builders, sponges, algae and corals experimenting with fresh designs. From ruin comes renewal. On land, the scene is stark. Gone are the vast coal swamps and towering lycophytes of the Carboniferous. In their place, landscapes are sparse, dotted with hardy seed ferns and conifers. These plants are more resilient to dry conditions, able to thrive in soils where water is scarce. The greenness of earth is thinner now, but it persists. Each leaf that sprouts, each root that digs into the ground, is an act of defiance against the silence. Among animals, the survivors include small reptiles and synapsids, the latter distant ancestors of mammals. While many great predators vanished, creatures like Lystrosaurus endured. Picture it, a squat, tusked herbivore with a beak-like mouth, waddling across dry plains in search of plants. Fossils of Lystrosaurus are found across multiple continents, suggesting it was one of the most successful animals of its time. In a world of scarcity, it thrived, its burrowing habits and simple diet allowing it to outlast many others. For a time, it may have made up the majority of all land vertebrates, a reminder that survival often belongs not to the fiercest, but to the most adaptable. The climate of this recovery world was erratic. Temperatures swung wildly, droughts alternated with floods, and the chemistry of the atmosphere fluctuated. Yet through it all, life endured. Reptiles began to diversify again, their eggs giving them freedom from water. Amphibians lingered in rivers and lakes, though diminished. Insects repopulated forests and plains, buzzing through air still heavy with volcanic haze. Step by step, ecosystems rebuilt themselves, fragile but growing stronger. Imagine standing in a Triassic dawn just after rain. The soil is damp, plants glisten with moisture, and a Lystrosaurus snuffles at roots near a stream. The forest is sparse, its trees thin and widely spaced, but birdsong has not yet arrived, and mammal cries are far in the future. Instead, the air hums with insects, their wings catching early light. The earth feels subdued but alive. It is a quiet resilience, a whisper rather than a shout, but it is enough. This recovery set the stage for what was to come. The reptiles that survived would diversify into new lineages: archosaurs, ancestors of crocodiles, pterosaurs, and dinosaurs. The synapsids that endured would, over immense spans of time, give rise to mammals. The oceans, too, would become homes for new predators, from ichthyosaurs to plesiosaurs. From the edge of silence, The seeds of future grandeur were already sown. Scientists trace this recovery through layers of rock. In strata just above the extinction boundary, fossils are rare, the stone almost empty. But as layers build upward, diversity returns. New species appear, strange and experimental, unlike anything before. Footprints in mud show animals wandering across barren plains. Plant pollen trapped in sediments reveals forests returning, conifers spreading across dry interiors. Slowly, life's handwriting becomes legible again. It is tempting to imagine extinction as final, as a door closing forever. Yet the history of Earth shows that each ending is also a beginning. The great dying erased worlds, but it also cleared the way for new ones. Without it, perhaps dinosaurs would never have risen. Without it, perhaps mammals would never have emerged. In the emptiness left behind, possibilities unfolded. Close your eyes and breathe in this quiet interlude. Hear the faint rustle of leaves in a sparse forest, the trickle of a stream cutting through dry soil, the distant grunt of a Lystrosaurus foraging. It is not the bustling symphony of earlier ages, but a softer melody, one of recovery and persistence. Life does not rush, it takes its time, building again from what remains. And so, before the dawn of Pangea, the earth waits in this fragile balance, healing itself, preparing for a new chapter. The scars of the past remain, but from those scars rise shoots of possibility. And a question lingers, soft as the first light after a storm. Does resilience come from strength, or from the quiet ability to endure, to wait, to begin again? Picture the Earth about 250 million years ago. The scars of the great dying are still etched into stone, but the world is stirring once more. Reptiles roam sparse forests, insects buzz in the air, rivers cut across dry plains. And beneath all of it, the slow, ceaseless movement of tectonic plates continues, pulling landmasses together. Gondwana in the south and Laurussia in the north drift toward one another, guided by forces too deep for eyes to see. Slowly, patiently, the continents knit themselves into a single vast land, Pangea. From space, had anyone been there to see, Earth would look astonishing. Nearly all land is fused into one enormous continent, stretching from pole to pole. Around it spreads Panthalassa, the world ocean, circling without interruption. To the east lies the smaller Tethys Sea, a glittering interior waterway. The Earth has remade itself into a pattern both simple and immense. One continent, one ocean, one stage for life. On this new supercontinent, climates are extreme. Along the coasts, forests and wetlands thrive, watered by rains blown in from Panthalassa. But deep in the interior, far from the sea, deserts stretch for thousands of kilometres. Red sand dunes ripple beneath a searing sun, broken only by hardy conifers and small shrubs. The air is dry, the heat oppressive, the nights cold and empty. Few animals can survive such harshness, but those that do, early reptiles and synapsids, become masters of endurance. Imagine standing at the edge of one of these deserts. The horizon is endless, the wind carrying dust across the plains. In the distance, a group of reptiles move slowly, their bodies low to the ground, scales glinting faintly. Overhead, the sky burns with midday heat, but at dusk stars appear in a sweep across the sky, unbroken by clouds. It is a landscape of extremes, born of Pangea's immensity. Yet not all of Pangea is barren. Along its coasts, lush environments flourish. Conifer forests rise in the north, cycads and seed ferns dominate in the south, their fronds spreading wide. Rivers cut through valleys, carrying nutrients from highlands to fertile lowlands. In these places, life rebounds with vigour. Amphibians linger in shaded streams, reptiles hunt among ferns, insects fill the air with movement. Slowly, diversity builds again, the quiet resilience of life reshaping the world. The joining of continents reshapes oceans too. Currents in Panthalassa shift, circulating heat and nutrients differently than before. The Tethys Sea becomes a cradle for marine life, its warm waters rich with ammonites, bivalves and fish. In deeper waters, predators prowl, while on reefs, sponges and corals rebuild fragile communities. Though the memory of collapse lingers, the seas are no longer silent. They carry new voices, new possibilities. Scientists trace the formation of Pangea in the alignment of mountain chains. The Appalachians in North America, the Urals in Russia, and ranges in North Africa and Europe all tell of collisions that stitch the supercontinent together. Fossil evidence too confirms this unity. Identical species of plants and animals, found on continents, now separated by oceans, once lived side by side on Pangea's vast expanse. The puzzle pieces fit, not only in shape, but in life itself. To imagine Pangea is to imagine both isolation and connection. On one hand, species could travel across immense distances from what is now South America to Asia without crossing a sea. On the other, the interior of Pangea was so vast and harsh that it created barriers as formidable as oceans. Life spread and diversified, but always within the limits imposed by climate and geography. It was in this crucible that the ancestors of dinosaurs began to stir. Small, agile reptiles darted through forests, their bodies built for speed. Archosaurs, the lineage that would one day give rise to crocodiles, pterosaurs and dinosaurs, began to rise in prominence. Synapsids, too, continued their quiet journey, their forms slowly refining toward what would become mammals. In this world of extreme, survival was never guaranteed, but innovation thrived. Imagine walking along a Pangean coastline at dusk. The sea stretches unbroken to the horizon, its waves glowing with the last light. Behind you, conifers sway gently, their resinous scent carried on the breeze. From the shadows, a reptile emerges, its eyes catching the fading sun. It pauses, listening, then disappears into undergrowth. Above, stars ignite in a sky unpolluted, the Milky Way arching across an ancient night. The world feels both vast and intimate, its rhythms timeless, its changes slow but unstoppable. And so the earth, once scattered into fragments, has drawn itself together. Pangea is not the beginning of continents, nor the end. It is one chapter in a long cycle of assembly and dispersal, of gathering and breaking apart. Before Pangea, there was Rodinia, before Rodinia, Columbia, Nuna. After Pangea, others will come, and still others will follow. The earth is a restless artist, forever rearranging its canvas. As you breathe softly, let the image of Pangea settle in your mind. A single land under a single sky, bordered by a single ocean. A world both unified and divided, fragile and enduring, scarred and yet alive. From this stage, the dramas of the Triassic, Jurassic, and Cretaceous will unfold. Dinosaurs, mammals, flowering plants, and eventually us. But that is a story for another night. For now, we close our journey through the worlds before Pangea. We have walked across Rodinia, drifted through Snowball Earth, swum in the strange ancient oceans, stood in the first forests, and listened to the silence of the great dying. Each step reminds us that Earth is not fixed but alive, not permanent but always changing. And the final question drifts, soft as waves against the shore of Panthalassa. If continents can gather and scatter, if seas can bloom and vanish, If life itself can fall and rise again, what will the earth become in the ages still to come?